So in example 2, we are looking at another homomorphism, phi, a map from Z to Z3, defined by phi of n equals to n mod 3, and we want to show again that phi is a homomorphism, and we want to find the kernel. Okay, so first, to show that it's a homomorphism, we have to show that phi preserves the operation, and our operation here is addition mod 3. So let's take two elements in Z, and let's see what phi of m plus n is in this case. Well, phi of m plus n is defined as m plus n mod 3, and that is equal to m mod 3 plus n mod 3, and m mod 3 plus n mod 3 could potentially be bigger than 3, so we have to mod out again by 3 to get our result. So that's what phi of m plus n is equal to. Now let's have a look at what is phi of m plus phi of n. Well, that is m mod 3 plus n mod 3. And since this operation is taking place in Z3, so this addition right here is addition mod 3, because it takes place in Z3, we still also have to mod out by 3. We have to take our sum and mod by 3, and we see that these two things are equal, and so our operation is preserved, and so we can conclude that phi of m plus n is equal to phi of m plus phi of n, and so phi is a homomorphism. So now about the kernel. What's the kernel of this map? So the kernel of phi, if you like, you can pause the video and see if you can figure this out first. So it's everything in Z that maps to the identity in Z3. And the identity in Z3 is 0. And phi of n is n mod 3. So we want n mod 3 to be equal to 0. So we want everything that's equal to 0 mod 3. Now, what integers are equal to 0 mod 3? Those are all the multiples of 3. So we have 0 itself, 3, 6, 9, and so on. And then we also have minus 3, minus 6, and so on in the negative direction. So that is the kernel of this map. Everything that's a multiple of 3, when you mod by 3, you get 0, and that's the kernel of our homomorphism phi in this example.